Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a locus problem. So we have r equals 2 cosine theta, and we're going to try to graph the set of points that satisfy this equation. What are we talking about? Well, if you're new to complex numbers, go ahead and check out my lecture videos. And if you like algebra, number theory, and trigonometry problems, go ahead and check out my other channel, Cyber Math, Cyber with an S. So these kind of problems basically represent, these kinds of equations represent a set of points that satisfy a certain criteria, and they just form a certain shape, okay? And that's called a locus. So what do we mean by that? Let's go ahead and talk about some basics, and then we're going to get into the solution. First of all, if you have a complex number, z equals a plus bi, where a and b are real numbers and I is the square root of -1. Notice that -1 has two square roots, but we consider the principal square root to be I. The other one is, of course, -I, right? Because if you square both, you get -1. So one thing that you should never forget is the fact that I squared equals -1. That's super important. So a complex number can be written in a plus bi, which is called a standard form, or polar form, which looks like this. So the same z can be written as r times e to the I theta, where e to the I theta represents cosine theta plus I sine theta, thanks to Euler. Okay, so that's the Euler's formula. And we get the most beautiful equation from here. But let's go ahead and focus on this now, because our locus problem, we need to focus for the locus, right? Our locus problem is basically focused on r and theta. So what does this mean? So we kind of need to talk about the complex plane, the Argand plane, and plotting a complex number. So the Argand plane is just like the normal coordinate system. The x-axis is called the real axis, and the y-axis called the imaginary axis. And if you have a number like a plus bi, you can basically represent it as a point on the coordinate system where the distance from 0 is called r, or the absolute value of z, where z is a plus bi. Therefore, this would be the square root of a squared plus b squared. And then there is an angle that forms, right, between the real axis, the positive part of the real axis, and the vector that represents the complex number. So you can think of a complex number either as a point in the system, in the coordinate plane, or as a vector, because vector has a direction, right? So, and vector is a good thing because when we multiply by I, it is equivalent to rotating by 90 degrees, because this is where I is on the imaginary axis. Make sense? Cool. So now we can go ahead and break this down into the x and the y components. So let's go ahead and split it up. If this is x and this is y, we can safely say that, and of course in the first quadrant we're talking about the length and the coordinates values, but in different coordinates, in different quadrants, it's always the value, the coordinate at that point. Okay, so here's what this looks like. Cosine of theta is going to be from here x over r, so we can write x as r cosine theta. And sine theta can be written as y over r, and from here we get y equals r sine theta. And then of course we do know that tangent theta is y over x, which doesn't include r in it. And we also know that x squared plus y squared is r squared, because sine squared plus cosine squared is 1. Make sense? So put it all together, you got the polar coordinates, right? Okay, cool. And in polar coordinates, you can make lots of different graphs, which look really nice, like lemniscates, limosons. Is that limachon, limoson? Something like that. It's a French word, I think. Anyways, so let's get back to our work. So how do we use all this information to find something meaningful for our equation, which is r equals 2 cosine theta. So in other words, this is what we're considering. And the polar system, we basically have two things. R, which is the distance from 0, and theta is the angle. So when I write something like r equals 2 cosine theta, basically this is what I'm talking about. For example, if theta is 0, let's make a quick chart. If theta is 0, then r would be 2 cosine 0, which is 2. Makes sense, right? Hopefully. If theta is pi over 3, or maybe I should consider pi over 6 first, which is 30 degrees, then r would be 2 cosine 30, which would be root 3. And then if this is pi over 4, then that would be 2 times root 2 over 2, which would give us root 2. Notice that the values are decreasing. And then as you go up higher values like pi over 3, this would be 1. And then finally, maybe we can just skip some values and go to pi over 2. It'll be 0. So let's just try to visualize this a little bit. Most of the time when I teach polar coordinates, I tell my students, make a table and try to visualize what's going on. Of course, graphing calculator will do this for you, but you're not going to learn anything from it, right? By pressing the buttons on a calculator, what are you learning? Pressing the buttons on a calculator. A lot of people glorify usage of graphing calculators, blah, blah, this and that. No, not really. It's just stupid. It's meaningless, in my opinion. Anyways, I could be wrong. 0, when the angle is 0. So when theta is 0, you're basically here, and you got to pick 2 units. So let's go ahead and pick 2 units. Let this be 2 units, okay? When theta is pi over 6, so it's kind of like, I could probably do it like this. This is like 45 degrees, and maybe this is going to be like 30 degrees, okay? Something like that. And on the 30-degree angle ray, on the 30-degree segment, whatever, we're going to have root 3 units. So it's going to be less than 2, maybe 1.7-ish, something like this. And then on the pi over 4, we're going to get root 2, which is even smaller than that. So notice that we're kind of getting, starting here, and then we're kind of going like this. At pi over 3, we are hitting 1. So maybe pi over 3 is going to be something like this, and you're hitting 1. So notice that kind of looks like a curve, right? I mean, it is a curve. At pi over 2, you're going to hit 0. So what does that look like to you? To me, that looks like a semicircle, but to be sure, we need to do the math. But at least I show you between 0 and pi over 2 what that picture looks like. Of course, a lot of times there's going to be a lot of symmetries, and with polar graphs, you're going to be able to graph part of it and then just reflect it or just copy it or whatever. Okay, so let's get to work. R equals 2 cosine theta. And now we do know that x is r cosine theta. But wait a minute. I don't have r cosine theta. Yes, you do. You can have it. How? Multiply both sides by r. Uh-oh. Notability going crazy. Calm down, notability. R equals 2 cosine theta. And then we're going to go ahead and multiply both sides by r. And that's going to give us r squared equals 2 times r cosine theta. Now notice that r cosine theta is equal to x. Yay. So we can replace that with x. And this one with x squared plus y squared. And hocus pocus, abracadabra. That gives us what we need. You know how? Let's put 2x on the left. And then complete the square. Add 1 to both sides. And then hocus pocus, you're going to get what you need. This is going to be x minus 1 squared plus y squared equals 1. What does that look like? The equation of a circle with center 1, 0 and radius 1. And that's exactly what we have here, right? The center is at 1, 0 and the radius is 1. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.